All right, so we're going to talk about electrical signals then. And when we talk about electrical signals in nervous tissue, it has everything to do about concentrations of ions on either side of the nerve cell membrane. So when we look at the plasma membrane and the permeability of the plasma membrane, nerve cell and muscle cells are what we say are irritable. And irritable means that they can change the permeability of their plasma membrane to change the ion concentration. And when we change the ion concentration, we can affect the positive or negative charge that exists inside of cells. So it's important to understand when you're talking about ion changes, that you understand or review the different types of channels that are on the membrane. So remember, we have leak channels, which are non-gated. They're always open. And we need those for flow of ions, but they're specific to the ion that's flowing through them. For example, we have leak channels for potassium. Only potassium can pass through there. We have leak channels for sodium. Only sodium can pass through there. And what we find on nerve cell membranes is that there are 30 times more leak channels for potassium than there are for sodium. So just like if you were going into a concert and there were more doors for girls compared to guys, what would we see a flow of into that concert once they open the doors? More girls coming in than guys, right? Because there's more doors, right, for girls compared to guys. So same thing with sodium and potassium. If gates are opening for either of these ions, we're going to see a greater flow of potassium than we are for sodium because there's 30 times more leak channels for potassium compared to sodium. So keep that in mind. That's an important concept. And then we have gated channels. So gated channels can be either ligand gated, and ligand refers to any chemical that has to bind to that channel before it can open up. So ligand gated, in this case, what's the chemical that has to bind if you look in this diagram? Acetylcholine has to bind. And then what ion is flowing when acetylcholine binds to this channel in this diagram? Sodium, yeah. So acetylcholine binds, it's just the key, and then sodium flows. And then voltage gated means that if we compare the inside to the outside, if the inside charge changes to a certain value, becomes more negative, at a certain number of negativity, that channel will open. Or if it becomes positive inside the cell, at a certain value inside the cell of being positive, this channel will open. So this is not an example of a voltage gated here. These are both examples of ligand gated. But keep in mind that voltage gated just means if something inside the membrane changes, it just automatically opens. So here's an example of a sodium channel. We see a little spot for a neurotransmitter like acetylcholine to bind, so therefore this would be a ligand gated one. And this is an example of what type of channel? It's always open, non-gated or leak channel. And here's one for chlorine, non-gated. So all cells have the same ions in the interstitial fluid and inside the cells, but only nerve and muscle cells can open up extra channels and change that flow and that concentration. So what do we find inside cells? Well, we find proteins. Proteins have a negative charge. And where do those proteins come from? Back when we studied the cell, where do we get proteins from inside that cell? How did they get there? Yeah, what you eat, you break it down into amino acids. Those enter the cell, and the cell turns them into something else, right? What organelle in the cell is in charge of making proteins? Ribosomes, very good. And with the help of the rough ER and the Golgi, right, to package and modify those? Yeah, so those proteins were made inside the cell. They're stuck there unless they're due to release them by maybe exocytosis, right? We talked about that's how large molecules leave the cell. So they're not going to fit through these channels. And what does it say the charge is on a protein in this diagram? Negative. So we got a little bit of negative charge trapped inside the membrane here because of these proteins that are stuck there. So keep that in mind. There's a negative charge due to this protein, a lot of proteins inside the cell. All cells are making some type of protein typically, unless it's like testes or ovaries, they make fatty hormones. But in nerve cells, we're just gonna assume that there's negatively charged proteins trapped inside that cell, and then we have a variety of channels. We have chemically gated channels for sodium, potassium, calcium, chlorine, and we have voltage gated channels for sodium, potassium, and calcium. So these are key ions, and we're gonna focus primarily on sodium and potassium. But when you get into the muscular system, and looking at the synapse, we're gonna see the importance of calcium as well. So again, when we look at the permeability of potassium and chlorine, we can see that there's more potassium and chlorine combined, so that this membrane is 75 times more permeable to potassium and chlorine combined. So we see a lot of movement of those ions. Another player in the membrane that it's important to understand to build this foundation of understanding the action potential is the sodium-potassium pump. And do you remember what direction things move with the pump? With every cycle of the pump? I have a little animation here we can watch. Just watch it here. Where did my animation go? All right. This is being a little stubborn here. Sorry about that. Let's see. Let's go here. I wonder if McGraw-Hill took their stuff away. Here we go. Good old YouTube. Okay. So what you just saw there is it grabbed 3 sodium, right, from inside the cell, and it's going to dump it outside the cell. And it's taking 2 potassium and bringing it inside the cell. So because of the pump, and if you look back here, what came into play right at the beginning? Right here, energy. Because aren't we pushing these against their concentration gradient? We're taking sodium and we keep bailing it out of the cell and pushing it out of the cell. So where do we see more sodium then because of this? Because if the pump is doing its job outside the cell, and where are we going to see more potassium? Inside the cell. So we have a buildup. We have a concentration gradient of more potassium inside and more sodium outside. So what would happen then through the leak channels? Which way is potassium going to want to leak based on what the pump has set up? Does potassium want to leak inside or outside the cell? It's going to want to leak outside the cell, right? Because it's building up inside because of the pump. So if we open up a door, it's going to diffuse out from high to low concentration. And sodium is going to want to diffuse in, right? But now we said there's more leak channels for potassium than sodium. So what's the charge on potassium and sodium? They're both positively charged, right? So we have these negatively charged proteins inside the cell compared to outside. but we're going to see more of a flow of positive charge in or out based on what we know about leak channels for potassium. We said where is there a buildup? Which ion is leaking out of the cell? Let's start with that. Based on what the pump is doing, which ion is leaking out of the cell? Watch the pump again. Which one is being dumped into the cell over and over and over again? Potassium, right? Here we see potassium is being dumped into the cell. So because potassium is being dumped in, when you open a door, it's going to leak out because it's building up in the cell because of the pump, right? And if there's more channels for it to leak out than there is for sodium to leak in, would you agree that there's more of a loss of potassium than there is a gain of sodium through leak channels, right? Through leak channels. So we see more of a loss of positive charge because of all those leak channels and the negatively charged proteins that are stuck in the cell. So as a result, we have a negative charge inside the cell. So let's go back to our PowerPoint here. So we had this buildup of potassium inside. But if we compare the fluid inside to the fluid outside, it's neutral because if I add up all the ions inside the cell, the positively charged ions and the negatively charged ions inside the cell, you know, they're equal, right? But if I compare the outside, same thing, you know, the interstitial fluid is neutral, the intracellular fluid is neutral, but there is a difference across the membrane, right, from inside to outside. So we're going to talk about what establishes that difference. So the pump is making a concentration gradient for sodium potassium, right? More sodium outside, more potassium inside. Everybody agree with that? Yes? More leak channels for potassium to leak out. Everybody agree with that? Kind of established that, right? And then those negative proteins trapped inside are going to make it negative inside the cell. So because of these three things, the inside is slightly negative compared to the outside. Because of negatively charged proteins, more leaking potassium than gain of sodium through more doors for potassium. And that pump is constantly creating the gradient. What would happen if the pump stopped? What if there was no ATP, the cell died, and the pump stopped cycling? What would happen to this movement? It would stop. Yeah, it would stop. Because doesn't diffusion happen until both sides are equal? But the pump, if the pump keeps cycling, it's never going to be equal, is it? Because the pump is using energy to keep pumping sodium out and bringing potassium in. So as long as we have our pump, as long as we have ATP, the body can survive, right? And what does the body need to make ATP? Going back to metabolism. Remember glycolysis, Krebs electron transport chain? Glucose and oxygen. Yeah, if we cut off the oxygen, we're in trouble, right? So yeah, so this is what keeps everything going and alive. Okay, so resting membrane potential then is just when a membrane is at rest, when the nerve cell is not being stimulated, it's hanging out. We've got the sodium-potassium pump moving potassium and sodium. We have leaking of potassium and sodium through their leak channels, and we have these negatively charged proteins hanging out here inside. But again, you'll notice, see all the green potassium? There's more potassium inside because of the pump, and there's more sodium outside because of the pump. But again, through leak channels, we always see potassium wants to leak out because of the concentration gradient, and sodium will want to leak in because of the concentration gradient. So again, an excitable membrane, muscle and nerve cells. So when we're just hanging out, that negative inside the cell has a value of -70 in a nerve cell. And that negative value is because of leaking potassium, right? Is not offset by leaking sodium, because there's more leaking of potassium through those 30 times more leak channels than there is gain of sodium. And those negatively charged proteins, right? And all of that leaking of sodium and potassium is the result of the pump. So when we look at changes in resting membrane potential, if I open up a door for chlorine, chlorine tends to be concentrated outside the cell. If I open up a channel for chlorine, what is that going to do to the negativity inside the cell if I allow chlorine in? It would be even more negative. So we call that a hyperpolarization. Is it not in your packet? We can skip to a different one. Okay, let's just skip that one then, and we'll pick up where everybody else is at. You have this one, correct?
Yeah.
Okay, let's talk about this. Okay, so what causes that value, we said of -70, that's the inside of the nerve cell, is -70 when everything is functional. The proteins are there, leaking potassium more than sodium, and the pump is cycling. So we have this -70. How do I change that -70 and open up channels? Well, I can produce an outside stimulus. I can, if it's in the eye, if I shine light on those dendrites, that's going to open up channels and allow ions to flow. If I have sound causing a fluid wave in the inner ear, that's going to stimulate those cells in the ear to open up channels and change that membrane, that resting membrane potential. If I touch my skin, I can open up special mechanically gated channels that when I morph the membrane, it opens up channels and allows ions to flow. So any stimulus is opening up channels. So that's really important that you understand the concept here is a stimulus is opening channels in that membrane. So that if I change the electrical field near an excitable membrane, so if I stick my finger in a light socket, is that going to stimulate neurons and muscles throughout my body? Definitely. If I grab an electric fence, did I tell you that story? Remember the electric fence? So yes, we know that electrical impulses will open up channels, voltage-gated channels, and cause a change in that membrane potential. And then a chemical messenger on the surface receptor. What is the chemical messenger that we've been talking about so far, the most common one? In the ligand-gated channels, every example I've shown you, it's been the same chemical. Remember what that chemical was? Acetylcholine, yep. And the abbreviation for acetylcholine is ACH, capital A, lower C, lower H, ACH. And then imbalances in the leak pump cycle. So we have sodium-potassium pump, and we have leak channels. So if there's some imbalance in that, that's going to cause ions to flow. Okay, so the term depolarization. So when we talk about the inside being more negative than the outside, we have a charge difference, right? Negative inside, positive outside. We say that it's polarized. Polarized means you have opposites. Like a battery is polarized, right? It has a negative end and a positive end. You got to put it in your device the right way or electrons won't flow and you can't operate your device. You've heard of bipolar disorder, right? People that are bipolar, we use it kind of in funny terms too. Oh, quit being so bipolar, right? What does that mean? Extreme moods, right? Really happy, really sad. So opposites. So when we talk about the membrane being polarized, it means we have positive outside, negative inside. So depolarization, what are we doing? Depolarize, so we have positive and negative, where we're making them less separate from each other, right? So what happens when we depolarize, we make it more positive inside the cell. So anything that causes positive ions to flow into the cell or negative ions to flow out of the cell, wouldn't you agree that would make it more positive inside? So that's what a depolarization is it becomes more positive inside the cell. Yes?
What is the electrical charge outside the cell? Is that usually negative or positive?
With that, we're only comparing inside to negative. So the difference between the two is -70.
Okay.
So it's not a strict value, but it's just the difference in charge is -70. Good question. Okay, so anytime it becomes more positive inside the cell because of flowing ions, so if I had a voltage-gated channel for sodium that opened up at a certain value, sodium wants to flow in. Everybody agreed with that, right? Because we have all the sodium built up outside the cell. If I open up a channel, an extra channel for sodium, it's going to flow in. And because of that flow in of positive charge, this -70 value that's sitting at a resting neuron, that's gonna change, and it's gonna go from -70 to -60 to -55 to -20, all the way up to 0 and then beyond, right? If we keep things flowing in, it would become into the positive range. So we call that a depolarization. Repolarization would be if I shut those doors and I'm positive, I'm climbing in the positive range, and then I shut those doors, and now I open up a channel for potassium, let's say. Where does potassium want to flow? In or out? Out, because it's built up inside from the pump. So if I repolarize, now I'm making it negative inside the cell again. So a repolarization is going back down to that -70 value. So here we can see we have a sodium channel is closed, no more sodium can come in, but potassium channel open, so we have all this flow out because of the pump built it up in the inside, so it wants to flow out the minute we open up an extra door. So we always have the leak channels, but this is a voltage gated channel that happens when the inside becomes a certain value, and in this case of a nerve cell, when it hits +30 inside, when it's +30 inside compared to outside, these are signaled to open. When these are signaled to open, this happens, this voltage gated sodium channel, because notice this is not ligand gated, so this only opens when the ion concentration inside compared to outside is -55. So this is a -55 voltage gated channel, and this is a +30 voltage gated channel. So we have to have a lot of positive flow in before this potassium channel is going to open up at +30. So at +30, that potassium channel opens, we lose all this potassium. What's happening to the inside of my cell? Yeah, it's becoming more negative, and it's going to drop back down. In some cases, as it's dropping down, those sodium or those potassium channels are signaled to close at negative values, but they're slow to close. So if I look at an example like just about finished here. If I look at an example of a Black Friday special, and we say the first 100 people in get a free plasma television, people would be cramming the doors, right? And then when they open the doors, people would come rushing in, right? And then if they shut the doors slowly, would more than 100 people maybe sneak through that door? Yeah, that's what happens with potassium. When potassium is leaking out, like we can see in this example, when potassium is leaking out and it hits that negative value inside the cell that signals those potassium channels, those voltage gated potassium channels to shut, sometimes a few more potassium will sneak out. And if we get more potassium leaking out, wouldn't you agree that would maybe drop it below the resting membrane of -70? But then it flattens out, because once all those potassium channels are shut, it flattens. And then what's going to clean things up and get everything back to where it belongs again, so we're hanging out at -70? And those that are with me can answer this question. What is going to clean things up after the voltage-gated potassium and sodium channels are signaled to shut, and we got a little bit of hyperpolarization going on, so we have a little bit of extra potassium in there? What's going to clean things up and get everything back where it belongs?
ACH.
No, you're close. You're close. So we have a look. What? Yes, the sodium potassium pump is going to clean things up, get everything back to normal until an outside stimulus again. And again, light, sound, pressure, touch, temperature, whatever is going to open up channels, special channels specific to those stimuli on the dendrites, right, on the receptive endings. That's going to open up some channels till we get enough flow, and then we're going to see a change in our membrane potential. So we're going to talk about this graph the next time we pick up, but this is what we, just a summary, this is what we talked about. We're sitting out at -70. Some stimulus caused channels to open for sodium, making it more positive inside the cell. Voltage-gated channels open up till we get to +30. That stimulates those voltage-gated sodium channels to shut. Then the potassium channels open up at +30. and then we lose potassium and we repolarize back down, and then those are signaled to close, but they're slow to close, so a little bit of extra potassium sneaks out. So we have this area right here, which is called a hyperpolarization, which means we're more negative than resting membrane potential. And then what cleans things back up right here, what did we say? Brings it from this back up to resting?
Yes.
Yes, sodium potassium pump until another stimulus comes. And we'll pick up next time and finish that concept so you can see from beginning to end how this whole process goes.